Hello. Here is a classic example of how to use alpha beta pruning on this particular problem. So the game tree that we have here has one, two, and three layers, and the fourth one is all leaf nodes. Uh, Before we get into how to do this, let me give a quick introduction on why we need alpha beta pruning. Okay, so let us consider this particular problem where there is node A, B, C, and there are four leaf nodes. And let me just do a typical minimax on this. Okay, so the first thing we need to do is go from like the bottom to the top. So the value of B here is going to be the minimum. One second. Is going to be the minimum of 10 and 15, which is 10. Okay, now the key point to note here is the value of C is, if the number here is going to be less than greater than minus 5, let's say for example 10, then minimum of minus 5 and 10 is going to be minus 5. So if this be 100 or 1000 or any number greater than minus 5, since we are choosing the minimum, the value is going to be minus 5. Let's say the number we are going to choose is less than minus 5. For example, it's going to be minus 4 or minus 2. In that case, the value here is going to be minus 2. So essentially, since we are doing a minimum operation here, the number can either be minus 5 or less than minus 5. So since we know this, I can just write the value here to be some value less than minus 5. So now when we go to this operator, we can see that it takes the maximum of 10 and any value between less than minus 5. So the number is going to be 10. So clearly here we can see that we do not care about the number here, because this minus 5 is the biggest number that can go here. And let's say this further had way more nodes. It's pointless to do all this search. From just this information and this information, we can get rid of all these searches. This like reduces the number of search we need to do in a tree by like a large amount. And this is essentially what pruning is about. So to kind of, it might be a little hard to keep this, like say there is a 10 here and there is minus 5, so this is useless. So trying to come up with that intuition for like really large trees is going to be hard, because you'll have to remember a lot of information. So instead what people have suggested is to use two functions called max value and min value in like for max nodes and min nodes. And remember two other values for each node, which is alpha and beta. So every node is going to have three values now. So the one is v. V essentially represents the number inside, and beta and alpha are like the maximum number and minimum numbers it can hold. So if we just remember three values for each node instead of one, we should be able to prune unnecessary parts of the trees. And that is what we're going to look at in the example above. Okay, all right. So let's go back to the main example that we'll be discussing here. So this is the node we want to calculate the max value of. And the next, so the main node has three actions: action 1, action 2, action 3. So there's one child here, another child here, another child here. So by notation, we call these links as actions: action 1, action 2, and action 3. And these are the results. So if you are in this node and you take this action, this is the result node. Okay, perfect. And we always start with alpha to be minus, we always start with alpha to be minus infinity and beta to be plus infinity, and we try to find the value of v. And we keep changing these numbers dynamically, and we remove useless parts of the tree. By useless parts, I mean the parts that we don't really need to calculate or dig into. Perfect. So we can see that there are only two operations that we need to do majorly. So one is like max and one is min. So these nodes, so this node will have to perform a max, which we'll call x. Like we'll call max as x operator and min as n operator, because like max and min. So these nodes here will require a min operation, and these nodes here will require a max operation. Okay. So every time we have to calculate a max operation, we will be calling this function. And right here, let's just break the function down. So this is something we don't have to worry about when we're breaking down like for nodes which are not on the leaf thing, because this just talks about terminal nodes. So this part is simple. If the node you are calculating max for is a terminal node, then just return the value. Straightforward. So for our cases, we mostly won't have to worry about this except for the terminal states. We'll mostly have to worry about these values. So what this talks about is, if you perform a max for a value, then look at all the actions. That essentially means we look at first this and then this and then this. We look at all the actions. So once we look at this, we perform a min value on the child. And we pass on alpha and beta. So alpha, beta, v, these two get passed on to the child, and we perform it recursively. So that's what's happening here. We have one check condition here, which is if the v that we are checking is greater than or equal to beta, then we return v. And we don't have to worry about continuing the function for other actions. Let's say you have action 1, action 2, action 3. And in action 1, we satisfy this condition. Then we return v here, and we don't have to worry about these children. So diagrammatically, what that represents is, let's say we are performing max here, and we realize here we return a v. Then we don't have to worry about these two, and we can just ignore these two nodes. And that is essentially what pruning is. So if we are ignoring nodes while we are performing a check on beta, then this is called beta pruning. Very similar to that function, we have min function. And if the check stops at alpha, then we call it alpha pruning. All right, let's continue working out with the example right here. So first, we need to start from we start calling functions from like the topmost node. So we assign alpha to be minus infinity, beta to be plus infinity, and v to be nothing for now. And we perform the max value. So max function, okay, we'll just stick to this slide right here. So we perform this. Okay, so we don't have to worry about this blue part for now, because we are only going to look at these nodes first, like all the nodes which are non-terminal. Okay, let's go line by line now into the function. So first, for this function, I am performing x, which is this function. For this node, I'm performing max value, and I'm looking at each action, which means each of these. And then, so first, I'll be looking at a equal to 1. So I'm essentially going down this path. And I'm performing result alpha and beta, so that is this. And for this min value function, which I'm calling right here, I am passing the value, and I need to pass on alpha and beta as well. So alpha here becomes minus infinity, beta here is plus infinity, because they are carried over from here to here. All right. So now what happens is, when I want to calculate the v here, essentially when I'm calculating min value, this function right here, so that calls this function. So now we are performing this function for this. And to keep track of where we are, let me just use like a green highlighter here. Right now we are in this part. and for this node we are calculating min value, so that goes down to this and this. So for this function I'll use a different color. So in the min value again I do the same thing for each action, that is like for each of these branches I call the max value for the children, so that's like the max value of this, and I also pass on alpha and beta. So minus infinity plus infinity, and I don't have a b yet. Okay, perfect. All right, now I need to perform x, like the max value function on this, but I know that this one is a terminal. Is it a terminal state? Oh, not really, not yet, not yet. Okay, this state right here is not a terminal state yet, but what I do is we will look at each of the actions here, right? So I look at this first, one action at a time. So I look at this action, and the value there is 12. So this line is going to be v is max of v and the value of that node, which is 12. So right now I don't have any value for v, so I'll just assign v to be 12. So v right now becomes 12. I just made an update here. Okay, so I'm done with this. Now we check if v is greater than or equal to beta. Like after this line, I'm checking this line, v greater than or equal to beta, which is not true because v is 12 and beta is infinity. So this line is not happening, and I make alpha to be maximum of alpha or b. So alpha here becomes 12. All right, perfect. Now I'm performing action 2. So for that, we're again going to perform this line now. V is max of the current value of v is 12 comma minus 7. Minus 7 is the value of the child. So we see this is still 12, so this is not going to change. So v remains 12. So now this line, is v greater than infinity? No, it's not. So it's not. And alpha is still like the max of 12 and 12. Like the values that I'm using here are from here. So it doesn't change. So it's perfect. We can go to the next branch. Now we are in this branch. We're doing this branch right now. So what we'll do this line now, v is max of current value of v is 12 and 14, which is the child value, and 14 is bigger. So we make v is 14 now. I've made the change here. So okay, we check this. 14 is greater than or equal to infinity, which is not true, so this does not happen. So now alpha is max of 12 comma 14, so alpha becomes 14. I made that change there. All right, perfect. So that essentially means that this call that happened from here is done. So this call right here is this line. So the v value here is what this function returns. This function returns v here. So the v here is being returned now. 14 is being returned. So that is, so here I call this, and the function this is returning is 14. So that is essentially this line. Since there's nothing here, the minimum is 14. So I should make v as 14 for the function where we call min value. So now here this becomes 14 from this line. Okay, so now we check if v is less than or equal to alpha, which is not true because alpha is minus infinity. And then we make beta as minimum of beta comma v. Beta is plus infinity for now, so this becomes 14. I just made the change here. Alright, so now we finish this for action 1. We need to do the same thing for action 2, which is right here. So let me highlight it with a color. We are right now here, the gray highlight. Okay, alright. So let's perform the same thing for this one. So for this node right here, we are going to perform an x function, a max function. And that is what is going to be returned as part of this. Alright, so let's do that. So for this function now, it's not a terminal state, so we don't have to worry about that. And we have 3 actions, 1, 2, and 3. And let's perform this action now. So for this action, which is right here, so we first, also when we're calling this right here, we do pass on the value of alpha and beta. So alpha is minus infinity, beta is 14. Alright, so now we perform max value on this node with this. So very similar to what we did earlier, we perform these 3 lines. So first v is max of v, which is, we don't have any value for v right now, and the child value, which is 7. So v becomes 7. This is from this line. So I should assign the value of v to be 7 here, and we finish this. Is v greater than or equal to beta? Beta is 14, v is 7, so this is not true. So this is done. Now we're right here. So alpha is max of alpha and v. So alpha is max of minus infinity and v. So these values I'm taking from right here. So alpha becomes 7. I'm going to change it right here. Okay. Now we're going to look at the next action, which is right here, which is minus 15. So the same lines. So v is max of the current v value, which is 7, and the child value, which is minus 15. So this is 7. So v is going to stay 7. Now this line, v greater than or equal to beta, is false. So this line, alpha is max of alpha, which is 7, and v, which is also 7. So this is 7. So nothing really changes. Perfect. Alright, so now this is also done. We are in this child now. So we'll do the same thing again. V is max of current value of v, which is right here. So 7 comma the child value, which is 19. So v becomes 19. So I need to change the value of v right here. I've changed it right here. So once that is done, I check if v is greater than or equal to beta. So 19 greater than or equal to 14. Yes. So we return v here. We don't update alpha. We return v. So that essentially means that this thing right here returns a value of 19. Oh, sorry, not here. So this return is part of the max value function we called, so which is this one. So that means we return 19 here. So this path we have explored. So this is not yet pruned. Even though we've done this, it is returning v based on beta. There are no further blocks here to be ignored. If, let's say, if there was one more here, that would have been pruned. But right now we have entered all the three actions, so no action is pruned yet. All right, so this returns 19 here. All right. If you made it so far, then that's cool, because everything else is going to get like mostly pruned. So this is like the hard part. You've made it, so congrats. So the value that this returns is 19. So this is part of the end function we called here. So we are at this position right now. So v is minimum of the current value of v, which is 14 for this node, comma 19, which is what's coming right here. So v will stay 14. And is v less than equal to alpha? Yes. No, sorry. No, because alpha is still minus infinity right here. All right. And then the last line is beta is minimum of beta and v. So beta is minimum of beta and v. So beta still stays 14. All right. So now we enter this path. So when we're entering this path, we give alpha and beta values from the parent node. And so right here, we need to perform x. So we're back here. So now we look at each action. So that's each of this. And hold on, this is where we start pruning the tree. So we have three values, three actions, and we perform these lines. So first, v is max of the v value currently, which has no value, comma 9, which is the child value. So v becomes 9. We check if v is greater than or equal to beta, which is false because 9 is not greater than or equal to 14. So the 9, 14, all these values come from here, because right now I'm performing max value, which is x, on this node. All right. And then I check if I update alpha with max of alpha and v. So alpha right now is minus infinity, v was 9, so alpha becomes 9. All right, cool. Again, let's go to the next child, which is right here, and we perform these lines of code again. So v becomes max of v, which is 9, comma the child value, which is 16. So v becomes 16, and I'm updating the value of v right here. And then I check if v is greater than or equal to beta, which is true. So this is happening right now, and we return v for max value function. So right here, we are returning a value without exploring all the... So we've entered this one, and we are returning v's value to be 16. But if you notice, we are not going to explore this at all. So this Right here is an example of beta pruning. Let me use red color here. Beta pruned. Okay, all right. So let's go back to this function now, which is obtaining a value of 16 in this line. So let me erase this. So v is min of current v is 14 comma 16. So v stays 14, which is the v right here. We're performing this from here. And then the next line is if v is less than or equal to alpha, which is not true because alpha is minus infinity for now, and beta is minimum of 14 and 14. So beta stays the same. All right, so what essentially has happened is we're done running this child from the main first function that we called. So this is done and it returns v. So this returns a value of 14. All right, so now we're done with this whole side. Now we move to this. So this is going to be a part of this function here. So this function is a part of this function. And so we just finished this line. So this return of 14 is from this function right here, the min value. So let's do this. V is max of, so we have no values for v here. So max of I comma the returned value. So that's 14. So v becomes 14. I have made the update here. And then is v greater than or equal to beta? No, because beta is still plus infinity. So this isn't happening. And we go to here, and since alpha is minus infinity, we take maximum of minus infinity and 14. So alpha becomes 14. Okay. So now this part of the action is done. We enter this. Okay. So when we enter this, we do this again. So we do min value of the child and we pass on alpha and beta. So there's going to be an alpha beta value here. 14 minus infinity, and v does not have a value yet. So now we go here and we call the min function again. And so the min here will have these three actions performed. So we'll go to this action first and we pass on the value of alpha and beta. So alpha is 14, beta is minus infinity. So let me quickly, just to remember which operation we're doing. So this is one operation and the next subfunction has this operation being performed. Okay, so right now we are here and we need to perform max value. We need to perform max value here. All right, so action 1, which is this action, and we perform the whole operation again. So v is max of nothing and minus 12. So v becomes minus 12. And then is v greater than beta? Is I made a mistake. So beta is going to be plus infinity. I'm sorry, from here. It is plus infinity and beta is plus infinity here. So is v greater than or equal to plus infinity, which is it's false. So we go to the next line, which is alpha. So alpha is going to be max of alpha and v. So alpha is going to be max of, so v is minus 12. Alpha is going to be max of 14 and minus 12. So alpha stays 14. So this is done. All right. Okay, now we explored this action. I'll just put a tick there because we're opening it. So now v is max. We perform these three lines again. Max of minus 12 and 5. So v becomes 5. We are not changing beta yet, so is v greater than or equal to beta? V is 5. Beta is plus infinity, so this is false. And then alpha is max of alpha and b. Alpha is 14. V has become 5. So 5 and 14. 14 is bigger, so nothing changes. So that's done. So we have one more action left. For this, we explored this, and now we're exploring this. So how are we going to do that? So we start with this line. V is max of 5 and 12. So V is going to be 12. Is V greater than or equal to beta, which is false. And alpha becomes the bigger value. So alpha is still 14. So we just make that change here. All right, perfect. So the value that is returned here is V, which is 12. So now we are back in this function, which is the min function, n function right here, and we are in this line. So we change the value of V as minimum of, there's no value of V right here, so I'll just put like 5, and the return value here for this function is this right here, which is 12. So V here becomes 12. I have made the change here. And then we check if V is less than or equal to beta, alpha, sorry, this line, which is true. So we have to return, so this is part of the min value here, so this is part of this function. So we return the current V, which is this, so we return 12. So we see that this function is completely done and we don't have to explore these trees at all. So that's pruning, and since we did it on an alpha condition, this is alpha pruning. So I will highlight the trees that we prune with it. So this is beta pruned, this is alpha pruned, this is alpha pruned. So we're back here. So this gets a value of 12, which goes right here. And this is part of the max function, so essentially we must be in this line. So V is max of V is max of the current V value, which is 14, and the V value that is being passed here, which is 12. So V remains 14. Is V greater than or equal to beta, which is false. And alpha is still the maximum of 14 and 14, so alpha stays 14. So now we explore this side. Was this the color? I was probably using the other color. Now we explore this. So we pass on to this. We pass on the alpha beta values, which is 14 and infinity. So now for here, we perform the min function. Let me erase these for clarity. Alright. So now part of this, I call the min value function right here. is not the terminal state, so I just need to look at all the actions, which is 1, 2, and 3 actions. Let's look at the first action and call max there. So I am right here now. Okay, so I pass on the values of alpha and beta. So for this node right here, which is we perform these 3 lines because it's max value here, x node here. So first v is max of nothing, and the child node, we are right here now, so minus 17. So v becomes minus 17. I've updated the value here. And then is v greater than beta? V is minus 17 is not greater than beta, so this line nothing happens. And alpha is maximum of alpha and b. So alpha is maximum of 17 and 14. So alpha stays 14. Okay. So now we enter the next branch. V is max of minus 15 and minus 17. Minus 15 is right. So I change this to minus 15. And the next couple lines, this nothing happens because beta is still infinity, and alpha is max of minus 15 and 14, so alpha stays 14. Now we explore the last action for this max function right here. So v becomes max of minus 15 and 10, which is the line right here. So v becomes 10, and these two lines don't change because v 10 is still less than infinity and alpha is still bigger than v. So the only change that happens here is v is minus 10. Perfect. So for this max function, we've finished all 3 actions. So it returns v now. So the v for this is 10, so 10 is returned here. So let's look at the return line for this function, which is right here. So v is min of the, which is like nothing because there's nothing here, and 10. So v becomes 10. V is made 10 here. And the next line is if v less than or equal to alpha, return v. So v is less than or equal to 14. So 10 is less than or equal to 14. So here we return v for the min value function. So here we return v. The value we return here is 10. So we see here that we've explored these paths, but we've not explored these two. So, and those are like conditions that are cut because of this line, which is alpha. So these two are alpha pruned. So we are back to the last line here for the max value function. So this line is part of this, so which is right here. So I do v is max of 14 comma 10. So 14 is from here, current v value, and the return is 10. So v stays 14. So v here, v stays 14. And is v greater than or equal to beta? Nope. So we don't do this, and alpha is the maximum, 14 of 14, alpha stays 14, and so we return v here. So the value of this is returned. So the final value of this is going to be 14. And this is beta pruned and these are alpha pruned. Thank you.